Here I'd like to share with you a really quick tutorial on the extraction of regular branches of log-type function. The technique is essentially the same as for power-type functions, but still there are some small differences, probably for inexperienced learner it's worth discussing. So here is our function. W of z is equal to the logarithm of z plus 1 divided by z minus 1. The branch cut is a segment from -1 to 1. And the regular branch is fixated by the condition that f of x is real for x real and greater than 1. The assignment is to find the value of w at point plus I0 and at point minus I. Well, first of all, let's consider our function under the logarithm. We denoted g of z, and it's z plus 1 divided by z minus 1. It has 1, 0 at point z equals -1 and 1 pole at z equals 1. And as a result, those are the branch points of our log function. So the branch cut connecting them seems to be perfectly legitimate. So let's draw the complex plane. And I leave it up to you to prove that this finite branch cut does indeed define a single valued function in the complex plane. And now let's find the value of our function at point plus I0. As usual, we choose some reference point on the real semi-axis x0 greater than 1. And we know that at this point the logarithm is well defined and real. And now let's connect our reference point with our destination point plus I0 with some contour. And now we trace the change of the argument of our g function as we move from reference point to the destination point. As we see, our g of z function consists of two simple complex numbers, z plus 1 and z minus 1, which can be easily interpreted as arrows in the complex plane. So first of all, the number z minus 1, it's the following arrow, and it rotates by angle pi in the counterclockwise direction. So delta argument of z minus 1 is equal to pi. The number z plus 1, on the other hand, doesn't undergo any rotation, it just sways a little bit and then returns to basically its original position. So delta argument of z plus 1 is 0. Then the change of the argument of g function is the change of the argument of its numerator minus the change of the argument of its denominator. So it's 0 minus pi. We obtain negative pi. Now we employ our standard formula for the regular branch of the log function. F of plus I0 is equal to the logarithm of the modulus of the ratio. And the numerator is 0 plus 1 divided by 0 minus 1. And denominator is x0 plus 1 divided by x0 minus 1. Plus the value of our function at point x0, log of x0 plus 1 divided by x0 minus 1 without modulus sign, and minus I pi. And since x0 is greater than 1, we can remove modulus sign in the first expression, and we obtain the logarithm of x0 minus 1 divided by x0 plus 1, plus the next logarithm, and minus I pi. And now we see that our x0 dependent logarithms cancel out, and we are just left with minus I pi. And here's the answer. Now let's address a point minus I. And again, we draw it in our complex plane and connect it with our reference point with some contour. And now arrow z minus 1 rotates in the clockwise direction by angle 3 pi by 4. So the change of the argument of z minus 1 is minus 3 pi by 4. The arrow z plus 1 rotates in the same clockwise direction, but by angle pi by 4. So the corresponding change of the argument is negative pi by 4. And hence, the resultant change of the argument of g function is negative pi by 4 coming from the numerator minus negative 3 pi by 4. And we obtain pi by 2. And once more, we employ our general formula for the regular branch. F of negative I is equal to the logarithm of the modulus, or the following ratio. Denominator minus I plus 1 divided by minus I minus 1. And the denominator is the same as the previous one, x0 plus 1 divided by x0 minus 1. Plus the same logarithm as before, and plus I pi by 2. And now again we can easily simplify the modulus sign under the first logarithm. We see that the modulus of the complex number in numerator is simply 1. So the whole thing is simplified as x0 minus 1 divided by x0 plus 1 without modulus sign, as before. Plus the next logarithm, and plus I pi by 2. And again our x0 dependent logarithms cancel out, and we are left with our final answer, I pi by 2. So this is how things works for slightly more advanced log type functions. So I hope you got the general idea and won't have any trouble with the similar examples.